We got a lot of material to go through this morning, so I'll go ahead and get started here right away. I'll apologize ahead of time. We're probably going to be going through some of this relatively rapidly because we would normally do this level of training in about a 4-hour training session, and sometimes we've even gone longer than that. So we're going to focus specifically on groundwater treatment issues today and how MIOX can help with those. Last time we talked very briefly about a lot of these. Some of that information will still be here. Some of the diagrams and flow diagrams and things will look familiar if you sat in on the last presentation. If you did not, that will obviously look new to you. But in addition to that, we're going to add some additional material in here. So some of the questions I get a lot of times are, when you talk about ratios of dosing, for example, how do you arrive at those ratios? And so we'll be going through a little bit of the actual chemistry involved and some of those details there. So I will be going through a brief introduction of MIOX and general system and chemistry information for you. For those of you who have not joined one of these in the past, we'll talk on that very quickly. I won't go into any excruciating detail on that because there are other presentations that if you go to our website, you can get to those and you can learn a lot more about the details of both of our equipment as far as data sheets and general information, as well as additional webinars from past months. Then we'll talk about iron and manganese reduction and or removal, hydrogen sulfide, ammonia, and we've added arsenic as well. That seems to be a fairly common question that it gets asked. We did not really talk about that too much in the last presentation. We did get a few questions on that in the last webinar, and so and then a couple subsequent follow-up emails. And so we'll be speaking about, or I'll be speaking about that as well. So what is on-site chemical generation? Very basically, we take salt, add water to it to create a brine solution, pass it through an electrochemical cell to produce a disinfectant. This is what a typical process train would actually look like. So you can see on the left-hand side, we would soften the water typically. Some of our systems actually do not require softening on the very small end, but on the larger systems we do. And that is because that calcium can come out on the electrolytic cell, become a maintenance issue. So by softening the water, it's very easy to condition that water in such a fashion that you get nice long run times with your electrolytic cell. Then we go into split that stream. Part of it goes into a brine tank where we make up our brine saturated brine. Part of that stream also goes into the back of the generator, so the generator will combine those two streams, automatically blend those two together at the right ratio, automatically control the electrolytic process, produce an oxidant that then goes into the oxidant tank downstream, which can then be dosed into whatever your application might be. So in the case of drinking water, for example, you may have two pumps in this location. One might be treating pre-treatment prior to a filter, for example, and then another one may be used for final disinfection prior to your clear well or your distribution and storage system. So very simple process flow. The only consumable that you're using in this case is food-grade salt. Systems are NSF approved as long as you use NSF salt. So if you use food-grade salt, you put that in the system, then the system is applicable for NSF approval. We make two system configurations. We make just normal basic bleach generators, which generate between, depending on the exact piece of equipment you're looking at, about 0.6 to 0.8% solution. These are strictly designed to generate the maximum amount of bleach for the lowest price possible. So these are just simple sodium hypochlorite generators designed to run at maximum efficiency. Where we start to get into some unique chemistries is our mixed oxygen series of generators. And we have another webinar that's very interesting. If you'd like to take a look at it, it talks much more about what these generators actually do and what they're producing. But to make a long story short, we use more power, a little bit different cell configuration to generate a stronger oxidant. And that oxidant is a combination of sodium hypochlorite and hydrogen peroxide. And so those two things combined with the trace hydrogen peroxide in there give it some really unique chemistry characteristics that we're going to be talking about more specifically and how they can do things a little bit differently in groundwater treatment applications here in just a couple slides. We manufacture a huge variety of equipment, anywhere from 1 pound per day, or about a half a kilogram per day of free available chlorine. All of our systems we rate as equivalent free available chlorine. So for example, if you have a system out there that's using 100 pounds a day of chlorine gas, you can look at one of our data sheets and just find which piece of equipment does 100 pounds per day of equivalent free available chlorine. We make everything from very small units of 1 pound per day. These look just like little home water softeners practically, all the way up to large systems that produce thousands of pounds a day per skid. And even the 1,000 pound per day units and larger are quite small as far as footprint are concerned. They, if you want to kind of get a handle on relative size, it would almost be like 2 refrigerators just sitting right next to each other. So very compact for a very large capacity. So just about any application you might want, from the very small to the very large, we've got a system that can do that. Our small systems, you can see a photo here down at the bottom of a skid-mounted unit. Those can also be skid-mounted for just easy shipping and installation. You literally just drop a power line to it, a few water lines and dosing lines, and you're off and running. So what are some of the reasons that people like on-site chemistry? Well, there's a lot of different reasons. One is it is extraordinarily cost-effective in most cases. There are a few spots where people are getting their chlorine for rock-bottom cheap price, but by and large, folks will see a payback of less than 3 years typically, including the capital and installation costs. So it is very, very cost-effective generally. But in addition to that, it's very safe. So we generate at below 1% threshold, so handling it is very safe. If you do have a leak in the oxidant tank, you pretty much just have to direct it to a drain. There isn't usually a necessity to put on hazmat gear and things like that because it doesn't have a very high pH. It's not very aggressive because it is below that 1% threshold. In addition, carbon footprint is a big issue these days. So if you're looking to reduce your carbon footprint at your water treatment facility, this is a nice way of doing it. If you are a large consumer and you're getting deliveries of bulk bleach, you can replace about 4 to 5 truckloads of bulk bleach with a single truckload of salt. So with that brief introduction, and again, I apologize for that very brief introduction. If you would like more information, I would very strongly encourage you to contact either us or go to our website and look at some of the other webinars. We'd be happy to run through some additional detailed information with you on that. So we'll jump right into groundwater treatment. So the issues we're going to cover today are iron removal. As you may know, that most jurisdictions are looking at a secondary maximum contaminant level of reducing your iron in that water to below 0.3 milligrams per liter. Manganese removal is somewhat similar to iron removal. The general process steps are the same. There's some little tweaks and quirks to it that we'll discuss in a second. That secondary contaminant level is about 0.05 regulated. Now, one thing to keep in mind about iron and manganese is they're not really a health concern. They are really more of an aesthetics concern. So if there is iron and manganese in the water, it isn't going to cause a health impact, but it will make the water very unappetizing and it can make it very unappealing looking. Waters that are high in iron, for example, may have a very brownish tinge to it, can stain fixtures, sink fixtures, toilet fixtures. Anywhere that water comes in contact with a basin or something like that can leave a residual behind, and will oftentimes result in complaints, either just complaints from your customers about the water quality, or in some cases, folks just simply won't drink the water. They'll go somewhere else, and may even go to other less safe sources, especially when you're looking at developing communities and developing countries and things like that. Hydrogen sulfide reduction. This is actually kind of an interesting application as well, in that at most levels in which it is found in drinking water, it doesn't present a direct health issue, but it has a horrible odor. It smells like rotten eggs. So you'll get a lot of complaints. Technically, if you're in a situation where the hydrogen sulfide gets high enough, you can run into some health issues. It can cause a mild laxative effect at higher concentrations. And also, if you're in an enclosed space with a shower or something, you could theoretically off-gas enough hydrogen sulfide to actually cause an inhalation hazard with your customers. In most cases, you're not going to run into situations where it's quite that high, but it's definitely something to look for. Predominantly, when we're talking about groundwater treatment, we're looking at odor control. Ammonia removal we'll be discussing a little bit, and arsenic as well. So iron and manganese removal, as I mentioned, they do tend to be very, very similar to each other. One huge advantage is the mixed oxidants in both of these applications. You can do them to a certain extent, certainly iron with a regular bleach generator. Manganese you can also do with a regular bleach generator, but I'll talk about some of the issues related to that here in a second. We are part of the solution to this. A common question we get is, will mixed oxidants or will your generators destroy iron and manganese, or will it put it into some sort of a completely soluble form that you'll never see again? The short answer to that is no, it does not. What it does is it oxidizes it and turns it into a solid, which can then be removed by further processes. So when you're looking at using a MIOX system for this, keep in mind it's not going to destroy those two elements. It's going to convert them into something that can then be removed through further treatment. Hydrogen sulfide removal is somewhat similar in a sense. With certain conventional chemistries, you can also turn that into a solid, which can be then filtered. But mixed oxidant has a really interesting property in that it tends to drive this all the way to sulfuric acid, which is a soluble form, eliminating the need for some complicated equipment. We'll talk about that in some more detail here in just a second. So iron oxidation converts soluble iron into something that can be filtered is the best way of describing this. So iron typically exists in the ferrous form, which is a +2 state, which is soluble in a groundwater supply. This can be converted to the insoluble form, in essence, by removing electrons, so through an oxidation process. So then that iron, when it turns into the +3 form, will combine into stuff that is solid and then precipitate out. So this does require an electron acceptor. The formula that you're looking at down below is the chemical reaction when you're looking at chlorine. This can also be done with oxygen as well, or potassium permanganate, or ozone, or something like that. But since we're talking about chlorine, this is the actual reaction that you're looking at. So for 2 irons, you take 2 iron, you add chlorine, so that's in essence 1 free available chlorine that you're adding, which is Cl2, plus some water, converts to 2 iron hydroxides, which is a solid form, and that'll drop out of the solution, plus 2 chloride ions and 6 hydrogen ions. Now, why this formula is important is it can actually be used to calculate an ideal dosage. So this reaction occurs very quickly relative to some other chemical reactions. This occurs very quickly. It's pretty reliable. About the only sort of twitch that you might run into is if you're on a surface water source or you have a groundwater that's under the influence. You might have some organically bound iron or some iron that co-precipitates with some other things and becomes a little bit more tricky to remove, requiring a little extra chlorine. But in general, this is a very easy reaction to manage. So if you take this formula, you can actually use this to calculate sort of your ideal dose rate or your stoichiometric dose rate, if you like technical terminology. And that's simply done by taking a look at the formula. So if we take the iron, for example, we'll focus on that one first. We can ratio the molecular weights of the iron and the chlorine in this formula to get your dose ratio. So the iron, 2 times the molecular weight of 55.8 and some grams per mole. So take 2 times those, which is 111.69. The chlorine, 2 times 35.45, which is 70.91. And if you ratio the 2 together, so you're looking at the ratio of chlorine to iron, you get a number of 0.635, which is a fairly common ratio that you may have seen out there. Now keep in mind, ideal rarely happens, so given your circumstances, you might want to be a tiny bit more conservative than that. For example, we'll typically assume about 0.7 parts per million is what you want to be dosing for the chlorine. So what would the process train look like in this case? Remember I said that it does convert it into a soluble form, which doesn't disappear. You then have to filter it. So here is a typical process train. You come out of the well, you dose some mixed oxidants or some hypochlorite into the pipe running over to your filters. These media filters can either be pressure or gravity. There's a wide variety of reasons that you'd pick one over the other. Some of the factors include things like what is the actual physical size of the plant. So very, very large plants will tend to go towards large gravity filters because they're more cost effective, while medium to small plants will tend to go towards pressure filters because you can use one pump to run through the filters and out to the distribution system. But there may be some other reasons to go one direction or the other. You may be site constrained on space. There may be you may just have a personal preference for whether you like closed tanks or open tanks. There's a whole variety of reasons that one might choose one over the other. But you will use a granular media filter on a lot of groundwater sources. This may just simply be loaded with 24 inches of sand media. You may, in some cases, go with dual media as well if that tends to be your preference. And the mixed oxidant is added just prior to that, or bleach. It oxidizes the iron into a soluble form, which then precipitates out of the solution and is removed through the filters and then fed to the storage and distribution tanks. In this particular scheme, you'll notice that I'm showing a second dosing point just prior to the storage tanks for residual. On some groundwater systems, they may actually eliminate that second dosing point and just simply overdose prior to the filters and carry that residual out to the storage tank. This is another kind of important thing to point out as well. So when you're sizing a system, not only do you want to take into account your contaminants, but you also want to make sure that you add the additional residual in there that you need for your distribution system. So for example, let's say you have 2 parts of iron and you multiply that by the 0.7, so you calculate out I need 1.4 parts per million of free available chlorine to oxidize my iron. You may also want an additional 1 to 2 parts for your storage and distribution tank. So you would add that for a total of 2.4 to, let's say, 3.4 part per million in order to size your total system consumption. So never forget about the residual when you're thinking about calculating the dose and the requirements that are for your system. Manganese oxidation is simpler, but the reaction is actually more complicated. Manganese technically has 8 oxidation states that it can exist in, but most commonly it'll exist in the manganese 2 form, or the manganese plus 2 in groundwater, which is soluble. And again, the soluble form is not toxic, but when it does oxidize, and the oxidation reaction tends to be fairly slow with manganese without some help, that can actually start to look like small, fine, dark purple or black particulate in the drinking water supply. And that can either evidence itself by what look like small specks of material floating around in the water, or it can stain, again, fixtures and just generally make the water look kind of unappetizing. Now, it can be converted in the insoluble form, again, which can be removed. And once again, you see a very similar chemical reaction down below. So manganese plus water plus chlorine gives you the soluble form of your manganese plus chloride plus hydrogen. And again, we can use this to calculate relative dosages. So you take your manganese, molecular weight divided by your chlorine in this case, and, your chlorine divided by your manganese, divide those two to give you a ratio of 1.29. And again, we typically will size for about 1.5 if we're looking at sizing a system. So we'll go just a little bit higher than that. Now, as I mentioned, the reaction is normally quite slow. So while iron, for example, can be oxidized fairly quickly, even with something as simple as oxygen, manganese will take hours, if not days, in the presence of something like oxygen. In the presence of something like chlorine, it can take a matter of hours or so, usually 2 to 3 hours if you're literally trying to just simply oxidize and filter and do something really simple like that. Potassium permanganate will react with it much more quickly. However, manganese also will catalyze in the presence of manganese hydroxide or manganese coating basically on medias. So what people often use is media either called manganese green sand, or you can coat conventional medias as well with the manganese coating to give you that catalyzed or autocatalytic reaction as well. So the process train will look very similar. So you'll have a process train where you're dosing your oxidant prior to the filters themselves, only this time you're going to load the filters with something different. The vast majority of the time it'll be a green sand or a green sand-like product. Green sand is technically a naturally sort of occurring mineral that is treated and then sold. However, the supplies are running pretty low on green sand these days, so you're seeing more and more products like Green Sand Plus, which is a manufactured product, and a bunch of different manufacturers have products as well, where this coating can be applied to the media either at the factory or in situ in the filters as well. And technically speaking, if you went ahead and just started one of these systems up with regular sand in it, over time that sand or anthracite for that matter in the filter will begin to take on that coating as well, and it's called the natural green sand effect. So even if you just throw in normal media and you start oxidizing ahead of it, it'll begin to coat itself and behave just like green sand media. And that's actually sort of an effect that people take advantage of when they're manufacturing these products. They speed that along with a combination of a couple chemicals and then force coat the media in a sense. So again, the process looks very much the same. You would dose prior to it. To start to oxidize that process, you take advantage of that catalytic effect to be able to have a very fast reaction in the filter media, and then you may dose again afterwards out to your distribution tanks. So keep in mind, when you're talking to folks about manganese reduction, you're going to also want to make sure that you're speaking to them about what sort of filter that they're choosing, and that becomes a very important discussion point with them. I should say, if they're already talking about using something like a green sand media, then you should be fine. If they're not thinking about using a coated media, then I would strongly recommend that you recommend it to them. It will make the system work much easier and be much more likely to succeed. The other thing I would also mention, just taking a step back, the mixed oxidants we've observed in the field do react much more quickly with the manganese. So we tend to see far fewer problems with breakthrough in the filters, whereas sometimes if you're using chlorine prior to even a coated media, you can see that you can have some difficulty based on what your pH of the water is and what some of the other chemistry of the water is as to whether or not that media actually works very well. So that's one of the reasons that you see a lot of people with this type of process train using potassium permanganate as a pre-treatment. So one of the things that we found is that mixed oxidants, because of that trace hydrogen peroxide in there, cause that reaction to go much more quickly and much more reliably, and it behaves very similar to potassium permanganate as far as treating manganese. So you can just substitute with a chlorine base and eliminate all that hassle of having to deal with potassium permanganate, which is highly aggressive, stains a lot. Folks don't like using it that much, and this offers you a really cost-effective and easy way of replacing potassium permanganate. And it works quite a bit better than regular bleach does, much more reliably than regular bleach does. Hydrogen sulfide presents some unique issues. Primarily, this will be caused, hydrogen sulfide gets into water source in situations where you have a well that has sulfur in the surrounding rock and the surrounding aquifer, and sulfur-reducing bacteria may be present in that aquifer. And the sulfur-reducing bacteria uses the sulfur as a food source, in essence, and a byproduct of its metabolic process is that it produces hydrogen sulfide. And that hydrogen sulfide gets into the water, it solubilizes into the water, and creates a rotten egg smell, even at very, very low dosages. People can sense or smell that rotten egg smell with just, in some cases, hundreds of a part per million of hydrogen sulfide. So you can have very, very low concentrations of hydrogen sulfide and still have customer complaints about a rotten egg smell. pH has a major effect on your ability to treat hydrogen sulfide. It's, as I mentioned, it's very noticeable at low concentrations, and it can also be more physically annoying at low concentrations. Or I should say, while it's maybe just what's the way to describe it? Just an aesthetics problem at low concentrations. At high concentrations, it can have other health effects as well. So as I mentioned, pH does have a very important impact on hydrogen sulfide and how one actually would go about treating it. So the hydrogen sulfide actually exists in two states in a water supply. So it can either be as a dissolved gas or a soluble product. And so the dissolved gas is literally just the dissolved H2S. And it's highly pH dependent. So if you take a look at this graph here, and we look at percent in the gaseous phase on the y-axis versus pH along the x-axis, you can see that at a pH of neutral, about only 40% of that is actually in the gaseous phase. If you go down into the acidic condition, most of that then ends up being in the gaseous phase. And as you go higher up, which is more common in the groundwater source, 8.5 pH, you can see that the vast majority of it is actually in the soluble phase, not in the gaseous phase. So now why is this important? Theoretically, if you had a groundwater supply at 5 pH, let's say, you could remove hydrogen sulfide very easily by just using a gas stripper. So you could run the water through, blow some air through the water, through the device, and you'd remove the vast majority of your hydrogen sulfide. At high pH, you can see that most of it is not removable. So if you had a water analysis that said, I'm at an 8.5 and I've got 0.5 parts per million of hydrogen sulfide, you can look on the chart here and you draw a line over and you can say, okay, my air stripper can, even if it's running 100% efficiently, it can only be expected to remove about 3% of the total concentration of hydrogen sulfide in that water. Now, the interesting thing about that is the moment you run that through a gas stripper, it re-equilibrizes, let's say, or creates a new equilibrium, and that small portion will then become gaseous again and start to off-gas, and people can smell it. So even the fact that only 3% is in the gaseous phase, that in many cases is enough for people to smell. So what does that mean? That means that you only have you have actually several different options to actually treat the hydrogen sulfide. So option one, you could theoretically lower your pH, degasify, and raise the pH back up. Some people do this. It can be very costly to do this. As you can imagine, if you have a significant flow, this will take a lot of acid to lower the pH, a lot of caustic to raise it back up, and they also present just a cost issue, but a safety issue, health and safety issue. You have large volumes of acid and caustic potentially around your plant, the chance for a spill and other managing issues, leaking tubing, leaking pumps, just routine maintenance on your chemical feed equipment, makes this a relatively unattractive option. It is still done in some cases where there isn't a lot of choice, but it is not the most attractive option. You can use ozone to drive the reaction all the way to sulfuric acid, which is soluble and non-odorous. And I'll actually take one step back here and kind of show you the two-step reaction that takes place. So the reaction for hydrogen to remove hydrogen sulfide is in fact a two-step process. So what can happen is the first reaction here on the very top, you have chlorine plus the hydrogen sulfide creates hydrochloric acid plus elemental sulfur. And so this is literally just sulfur, and it'll sort of look like a really fine, hazy, yellowy sort of color in your water if you have a high enough concentration. Eventually that'll settle out. And if the reaction stops there, you can do something like filter that out. You may have to use a little bit of polymer or something to try and get everything to stick together pretty well, sort of gum up the filters a little bit so that your sulfur comes out a little bit better. But if you have a strong enough oxidant, you can actually then take that sulfur and continue to oxidize it. So theoretically, you could take that sulfur, add 3 free available chlorines, plus some water, drive that all the way to hydrochloric acid, plus sulfuric acid. So the combined reaction is this one down here, this third reaction. So this takes those two and then goes ahead and calculates out, and you can use that to, again, calculate a ratio of 8.34 parts per million of chlorine for each hydrogen sulfide. So now going back to our options, one of the things that's a real challenge is regular chlorine does not do a very good job, if at all, of reacting with elemental sulfur. So elemental sulfur is fairly stable. It doesn't like to react very well, and you need a strong oxidant to drive that reaction all the way. So option number 2, you could certainly drive that two-step reaction using something like ozone. So looking back at this reaction here, instead of chlorine, here we'd be replacing with ozone, and you'd be looking at this reaction taking place using oxygen instead of the chlorine. Most common option that you see in drinking water treatment plants is to put in a degasifier to degasify as much of the gaseous phase as you can to reduce your total bleach cost or your total hypochlorite cost. Add bleach, and as I mentioned, I guess I didn't mention, but the reaction with bleach is still relatively slow even to get to elemental sulfur. Usually you'll put in about a 1 to 2 hour detention tank in there, and then filter through granular media filters the sulfur that has been formed. Or option 4, the mixed oxidants have been shown in multiple installations that it actually drives this reaction much in the way that ozone does. So it very quickly drives that reaction all the way through to sulfuric acid. So now why is that important? So if you're looking at a new system, for example, and you're going to attempt to address your groundwater or hydrogen sulfide in your groundwater, this is a typical flow scheme that you would probably be looking at. So you would come out of the water, you're going to be purchasing a degasifier possibly to remove as much of the hydrogen sulfide as you can, in essence, for free. Go to a detention tank underneath that, which will be sized for 1 to 2 hours. That may be out of steel, maybe out of concrete. Depends. It's going to take a fair amount of real estate. You're going to dose chlorine just after the degasifier, and then from there go to your filters. And once again, that can either be gravity or pressure filters to remove the elemental sulfur, and then finally out to your distribution and storage tanks. With the mixed oxidant process, this is what you're looking at. So using mixed oxidants instead of regular bleach, you can come out of the well site, just dose the mixed oxidants, and usually you just kick that up a little bit to maintain your chlorine residual as well, and then go straight out to the distribution tank. So in essence, you eliminate the having to purchase degasifier, storage tank, and filters, especially if you're looking at a new site. So it greatly simplifies and vastly reduces your cost of capital equipment. Another big advantage to this is that you eliminate the potential for having to what we term double pumping. So in this particular case, if you come out of the well, so the original case, you come out of the well, you go through your gasifier detention tank and through your filters, you're going to have either a pump before some pressure filters again to boost that pressure back up to your distribution system, or a pump downstream if in the case of if these were gravity filters. So you'd have to have a pump at the well and a pump prior to your distribution system. In this particular case, you eliminate that second set of pumps. So you can actually use your well pumps to drive through, to dose right into that stream and go straight into your distribution system. And frankly, for most well supplies that haven't been forced to filter or have other issues, this is normally what we'll see is happening. Somebody is running off of a well, they've been running this way for years, they haven't had any iron and manganese difficulties, but they're either seeing more and more hydrogen sulfide, or they're getting more complaints about hydrogen sulfide, and they're looking at a significant plant upgrade. So they would either have to go put in a lot of equipment in order to address it, or switch to something like mixed oxidants, and then just simply continue the way that they're doing, just add in an injection quill and a mixed oxidant system, and off they go. So very little impact on the plant operation. Now we'll be shifting gears, going to ammonia, and I will admit that ammonia is an incredibly complicated chemistry issue for breakpoint chlorination of ammonia, so I will try to condense this very much down into just a few sort of highlight slides. But ammonia can be accomplished in a variety of ways. Removal, and one of the questions I always get is, well, where is the ammonia coming from? Why do I see ammonia in my groundwater? And the most common cause of something like that is due to over-application of fertilizers, that ammonia can actually get into the groundwater supply from the recharge rate of the well. And so you'll see places like I live in Iowa, actually, most of the time here, and we see wells groundwater wells that have been great for years that are starting to see ammonia levels start to creep up year on year as they draw down those wells and the ammonia gets pulled into the recharge cycle. So it is a problem that you may not even have had in the past, but it's a problem that can start to creep up over time and may need to be dealt with. So it can be done in a variety of ways. You can remove with biologically activated filters, biologically active filters. So you may actually put in a conventional granular media filter, load it up with some carbon or some anthracite or something like that, normally activated carbon, and deliberately grow a population of bacteria on that filter media in order to consume and biologically process that ammonia. This can be effective, but in low concentrations, you may actually have to dose something like methanol in order to provide an additional food source to keep those bugs alive. It can also be a bit of a public relations challenge. So a lot of folks out there won't necessarily understand that you're using good bacteria to accomplish something in a drinking water treatment plant. The gut reaction of your customers can oftentimes be, I don't want bacteria in my drinking water treatment plant. That makes no sense, even if it's biological, or even if it's beneficial. So even though this is a process that can be used and has been used, it probably isn't quite as popular as some of the other options. So nanofiltration reverse osmosis can be used. Probably the two biggest challenges one runs into with those is that the operating costs can be high. They operate at relatively high pressures and can cost anywhere from about $90 to maybe $1.50, $2, 1,000 gallons produced to operate, which is a fairly high cost for a piece of process equipment in a plant. Or you can breakpoint chlorinate to convert that, in essence, oxidize the ammonia over to nitrogen gas. Disadvantage of those are it can require a relatively high volume of chlorine and can be a challenge to control as well, but in many cases can be the simplest and most cost-effective way to do this. I won't go into excruciating detail, and I will not go through every single one of these for you, but to put it mildly, breakpoint reaction chemistry is complicated and is not entirely defined. This is just some of the many reactions that can be taking place and some of the side reactions that can be taking place and intermediate reactions in the process of actually oxidizing the ammonia. This is another way of looking at it, and this comes from Javert and Valentine from 1992, and this paper was called Reaction Scheme for the Chlorination of Ammoniacal Water. So this is showing if you're starting with ammonia and you're looking to breakpoint chlorinate it, what are some of the different reactions and some of the different byproducts that can be formed during the breakpoint chlorination process. And as you can see, there's lots of different options, lots of different intermediaries, and it can be difficult on paper to actually say this is exactly what we think is going to happen. Now, one thing, if you're kind of a chemical nerd like I am, the more complication that you see in a reaction like this, what it tends to say is you're probably going to need to dose more than you think you're going to need in order to do what you want to do. So if you might be able to write out a very simple, let's say, a reaction and say, okay, I ought to be able to dose 7 parts, if I can write out a whole bunch of different reactions that are happening, likely I'm going to have to dose more than that. And that's what you actually see in ammonia oxidation. So even though it's very complicated, oftentimes the reaction path will be reduced through this variety of simplistic reaction steps up top down to this net reaction down below, where 2 ammonias plus 3 chlorines equals nitrogen gas plus 6 chlorides and 6 hydrogens, which gives you, and I won't go into the math again because you've seen it plenty of times, but gives you the ratio at the bottom of approximately 7.6 parts of chlorine to each part of ammonia, if everything was absolutely perfect and it did exactly what you thought it was going to do. In reality, you'll often see folks say that they recommend either 5 to 20 parts per million of chlorine be dosed per part per million of ammonia. In fact, I would say that in my experience, 15 was the rule of thumb that we would use most often when we were looking at just chlorine bleach, and that goes for just chlorine bleach or just chlorine gas. In addition, as I mentioned earlier, control of the system can be a little bit of a challenge. And I didn't cover this earlier, but the reason this is called breakpoint chlorination is because of this behavior, and this is also why it can be a bit of a challenge to control. So if you have ammonia present in the water and you start adding chlorine across the x-axis here, so this is generic graph, so this is just going from no chlorine that you're adding to higher levels of chlorine you're adding. If you begin to monitor that chlorine residual on the y-axis, you'll initially see that go up. So the chlorine residual will go up and go up and go up as you dose more, and then suddenly you'll hit the break and it will begin to decline. And at this point is when you are beginning to form your nitrogen gas and react that ammonia all the way. So ideally, as a plant, you're going to want to control right here. So you've basically converted most of it over to nitrogen gas, and you're at the low point of your chlorine residual. So you got to get up and over the hump and then control based on that low residual, which means that you're going to have to do some water testing, and you're going to have to do some things ahead of time to figure out approximately where you should be controlling. So now, why does mixed oxidant solution come into play here? And where it's really interesting is that mixed oxidant on ammonia-bearing waters has been shown to behave very, very close to the stoichiometric ratio. And in fact, in most cases, it's right on top. So we'll literally be seeing 8 parts per million, or 7.5 to 8 parts per million per part per million of ammonia in order to drive that break point all the way, as opposed to the 15 sort of rule of thumb that people typically use for regular chlorine bleach. And so what does that mean? That means that you reduce your chemical consumption by nearly 50% and your chemical cost by nearly 50%, meaning that you can put in a mixed oxidant system in and pay it off very, very quickly. ROIs on systems with approximately 1 part per million of ammonia can see a return on investment in 2 years or less in most cases. So the summary of our experience of the breakpoint reaction, some take-homes on this, is that the reaction tends to proceed at or near, or even in some cases slightly below, the stoichiometric requirement of 7.6, or the so-called ideal dose of 7.6, which is in sharp contrast with free available chlorine as bleach. The reaction also tends to be very fast, completed in approximately 20 minutes, or even less, with reactions with bleach tend to be much slower, which means it's much easier, much more reactive to control in your water treatment plant. One other thing I didn't go into excruciating detail on, but it tends not to form nearly as many chlorinous odors as well. So because it drives the reaction much closer to completion, you don't form nearly as many byproducts that cause those chlorinous odors. Finally, I'll talk about arsenic removal very quickly here. Can't believe it's already been almost 50 minutes, but this will be the last section we'll cover. And arsenic is kind of, in a sense, similar in a way you can think about it to iron and manganese, in that we are part of the solution in this case, but not the entire solution. But mixed oxidants, MIOX, is a simple, cost-effective first step in the removal of arsenic. So arsenic is a naturally occurring element that is found in groundwater sources. It's typically found in 2 forms, either arsenic 3 or arsenic 5. So arsenic 3 is the lower oxidized state. Arsenic 5 is, and I put in quotations, easier to remove because it kind of depends a little bit on what else you're doing with it. So, for example, a true RO membrane will probably get great removal of both, but if you go with something like a nanofiltration or a softening membrane, it'll remove the 5 much better than it will remove the 3. And also some co-precipitation processes work much better on 5 than they do on the 3 form. So oxidation often ends up being the first step in removal in this case, largely dictated by what you're doing downstream. Once you've oxidized it, you need to either co-precipitate it or sort of absorb it out with iron is the most common method and the most probably cost-effective method of doing this. You can oxidize it in a variety of different ways. It's actually fairly easy to oxidize. So ozone does it very quickly. Potassium permanganate does it quickly. Chlorine bleach, sodium hypochlorite, mixed oxidants all oxidize arsenic very quickly. Chlorine dioxide and monochloramines tend not to oxidize it if at all. And so if you are choosing a low-cost, easy-to-use oxidizer, probably out of this list, definitely out of this list, bleach and on-site generated bleach or mixed oxidant is by far the most cost-effective way to oxidize your arsenic. Iron, and I would say this is, of course, not the absolute, but the most common way of doing it in drinking water applications is then to use iron to remove that oxidized arsenic. In some cases, you may already have iron present in the groundwater source, and if that's the case, you'll get a double bonus here. So you'll add in your chlorine, your mixed oxidants to oxidize the iron. You'll add in a little bit of extra to take care of oxidizing the arsenic. And as that iron starts to precipitate out of the water and form the soluble iron, it'll actually drag out or sort of co-precipitate the arsenic along with it. If you have no iron in the water source, you can add an iron salt such as ferric chloride or ferric sulfate to accomplish the same thing. Alternatively, there are a variety of iron media, iron-based media that are out there, such as granular ferric hydroxide or other types of sort of precipitated iron media that can be loaded into a pressure vessel, and then the arsenic-laden water can simply be run through that pressure vessel, and it will absorb the arsenic out of the supply. One thing that's very nice about it is that it does bind very tightly to the iron, and in most cases that can be disposed of to landfill. There are probably a few jurisdictions around that don't like you to do that necessarily, but by and large, most of those iron-bearing medias or your backwashed iron is just simply landfilled or just run out to a red water filter or something like that to get rid of that iron and the arsenic. So it's a very simple process to use. Again, we're part of the solution. So if somebody's looking to take out arsenic, definitely mixed oxidants and MIOX products can be used for the pretreatment. So kind of in summary, I kind of went through a lot of that fairly quickly. There are a lot of the backup chemistries are involved in here, and we have a lot more information for you behind the scenes. If you're interested, you can certainly feel free to contact either your account manager or send in a request through the website. We'll make sure that we get in touch with you as the right person if you want some additional information on these groundwater stoichiometries and treatment. This is a cheat sheet I like to provide to people. This is sort of some guidelines that we would typically use to size systems, and you'll see there's the variety of contaminants on the left-hand side, and then the stoichiometric or the sort of the ideal dosing ratio that you would see in the center column here, and then conservative for estimating. So we would normally out of the box use these conservative numbers to estimate. And what I like to tell people, because sometimes I get questions of, well, if you see a lot of times 7.6 or 8, why are you assuming 10? I like to tell people that some of these chemistries can be relatively complicated. There can be additional complexities in there. And this is what I like to use for just the very first question. So somebody says to you, I've got a 2 million gallon a day water supply, or I've got a 5,000 cubic meter per day well source. I've got this much iron, I've got this much manganese, I think I've got this much ammonia. Roughly how big of a system do I need? And it sort of lets us very quickly come up with an answer for that says, okay, it's about X size. That means you're looking at a Vault series unit or a Rio series unit, and it's approximately this price. At that point, if you want to narrow it down a little bit more, it's very easy to do jar testing on these types of things. It's very easy to do jar testing, very easy to pilot. Especially groundwater sources are very easy to do because you're usually not overcomplicating with a lot of other treatment processes. If you're looking at something like this, then you can just do a simple side stream pilot if you need to. And we have handheld units that can be used for generating in the lab, so we can do lab testing. It can also be done on site. So it's very, very easy to test. And then from that point, you can narrow it down a little bit tighter. But at least these numbers will get you very close to the sort of the right starting point when that initial request comes in. And that's about it. And then one other thing I think I should probably mention is we do have some automatic calculators that we use in-house to help size these types of things. There are some other contaminants in there as well. So we also have things like COD and BOD and TOC, which are really more applicable to either wastewater, industrial, municipal wastewater. TOC is more applicable to drinking water applications. surface water applications. But there are other contaminants that we also have that if you tune into the surface water one approximately a month from now, we'll talk a little bit more about some of those ratios as well. And so a lot of that is available, also through tools that are available through your account managers, and we'd be happy to run any testing or any theoreticals for you that you might need.